Hey all, welcome back to Math for Machine Learning. So hope you guys all had a good Thanksgiving break. Today we're going to start talking about optimization. So let's get started. So optimization is pretty much at the root of a lot of machine learning problems. We try and reduce machine learning problems to optimization problems so that we can then solve the optimization problems and give you back the answer. So for example, if we're doing a linear regression with weights W, we can set up finding the best W as an optimization. We minimize the total squared loss. We can optimize for the best regularization strength, and we can optimize over discrete variables too. We can choose, for example, whether to include or exclude a feature in our model, and finding the best feature set is an optimization. And a lot of times, solving the optimization problem is the key computational barrier, at least, to solving our ML problem, meaning to getting good generalization error. So it pays to think about the best way to set up the problem and the best way to solve it. At the top level, we can split problems into two basic kinds: continuous problems and discrete problems. Continuous problems are with real valued parameters, and discrete problems are with categorical parameters. So like a regression is a continuous problem, and a variable selection problem is discrete. Another good example of a discrete problem would be, if you guys remember outlier detection and removal, we could have a discrete variable that told us whether each point was an outlier, and we could set up some optimization criterion to figure out which points to call outliers and which points to keep. And of course, you can mix between these two kinds of problems. You can have some continuous variables and some discrete variables, and that means you mix between the two types of solution algorithms. Another thing is that sometimes variables that seem continuous are actually hiding discrete behavior. So for example, if you have multiple local optima, that can be giving your problem an aspect of a discrete optimization, even if your parameters are nominally continuous. Or if you have discrete parameters, but those parameters represent a discretization of a continuous attribute, then despite the parameter being categorical, it might behave more like a continuous optimization problem. So how do we set up the problem? So one of the most common forms for an optimization problem in machine learning is this one right here. So we have some parameter vector, which I'm calling W, and we want to minimize over W a loss function, which I'm calling capital L. And that loss function is a sum of terms. So I've got L0 broken out here, and then a sum from little t equals 1 to big T of LT of W. And the idea would be that, for example, in a linear regression, the teeth little l would encode the teeth training example, and L0 would encode, for example, the ridge term. So in general, this optimization problem, it's got our problem data baked into it. So, you know, LT of W could be something like this. Let's get a spot on the paper. So if we have training data xt comma yt, right, for t equals 1 to capital T, we could have a training example where we predict yt should be approximately equal to w dot xt. That should be a like that. And we would like to minimize the squared error over all training examples. And so we set little lt of W to be that. And notice that little lt has xt and yt baked into it. They are hidden in the notation, but they're, you know, they remain. They're actually inside that, that little loss function. And then similarly, to get a ridge term, we could set L0 to be the ridge parameter times half the squared norm of W, or we could omit the ridge term by setting the first loss term to be 0. Another common example is maximum likelihood. So we have training data x1 through xt, and we set w to be the vector of parameters of our distribution. So we've often called that theta, but right now we're calling it w. And we set little lt to be the negative log likelihood of xt given w. And we could also do something similar by setting little lt equals minus log p of xt given w and y, sorry, that should be yt. I don't know why it keeps doing this. So that should be yt, and that should be xt, right? So this is the input for the teeth training example and the output for the teeth training example. And if we set little lt this way, it gives us maximum conditional likelihood as opposed to maximum likelihood. And then similarly, for maximum likelihood, we set the first term in our loss function to 0, or for maximum a posteriori, we set it to be the negative log prior. All right, so hopefully this should convince you that lots of machine learning problems can be set up as optimization problems. And if you're not convinced yet, you should leaf through the proceedings of ICML or NIPS, and probably at least 10% of the papers are about have some optimization problem described in them. Actually, probably more than that. Depending, I'd say maybe 5 or 10% of the papers are proposing a new optimization problem, and 90 or 95% of the papers have an optimization problem hidden in them somewhere. All right, so far all of these problems we've talked about are unconstrained optimization problems, meaning that so up here I had minimized the loss subject to a constraint that w had to be in some set C. And that's what we're going to be talking about this lecture. We're going to be talking about the unconstrained case. But in general, you could have constraints. So a good example of constraints might be, if you remember models, right? We derived that we wanted to maximize this function of omega, where omega is the precision matrix. Oh, I'm getting a question. I'm getting a question about the difference between this, which is in the notes, log p of xt given w, and this thing, which I just drew. So this here, which is in the notes, is describing a maximum likelihood problem. This here that I drew on the lecture is describing a different problem. It's describing maximum conditional likelihood. Right? So the difference is whether your training data is x1 through xt, meaning that you're just trying to fit a distribution to x1 to xt, or whether it's something like this, xt comma yt, where you're trying to fit a distribution to yt conditioned on xt. So it's a good question, right? These are two different problems where we set lt to be that versus that. All right, so going back to Gaussian graphical models, we wanted to do a constrained optimization. We wanted to maximize this subject to constraining some of the entries of our precision matrix to be 0. So we can do that either by leaving those entries as 0 and not considering them as optimization variables, or we can have all of them as optimization variables but try and enforce constraints that say that omega ij equals 0 for ij in some set z that are the coordinates that are supposed to be 0. And if you want to express that in the sort of standard ML optimization format before, you can take the loss terms to be like this. Right? In particular, you take the constraint set to be the set of matrices that satisfy the constraint that their ij entry is 0 for all of the entries. All right. All right, I'm getting people are saying it's freezing. I just want to. All right. I can't tell what it is that's causing the freezing. If I'm not back, if I'm not stopped freezing, I'll do the same thing that I did before of stopping and starting the stream. All right, so apparently I'm back now. Hopefully that's all good. I don't know what causes these freezes. I've tried to diagnose them, but without so much success. Anyway, let's get back to lecture and hope that everything keeps going well. All right. So unconstrained optimization problems are what we're talking about so far. Gaussian graphical models give an example of a constrained optimization, which is to say that we can try and optimize this function, which we can break up into a sum of terms, subject to the constraint that some of our precision matrix entries are 0. And we're going to be doing unconstrained this lecture, and constrained we'll come back to later. All right, so there's a lot of different problems, a lot of different variations that we can make of this problem. And of course, differences in the setup, these variations lead to differences in how difficult the problem is, and also what algorithms are most effective to solve it. So a full treatment of the different variations and all the different algorithms is probably beyond the scope of what we can do in this course. But here are some of the things that you can be looking out for. One is the problem low or high dimensional, meaning how many dimensions does the parameter vector have? If it's got a ton of dimensions, that rules out some of the optimization algorithms that scale poorly in the number of dimensions. How many terms are in the sum? So again, if there's, a billion training examples, that's different from a million training examples, which is different from 1,000 training examples. Are the individual functions differentiable, the individual terms in the loss function? Can you describe the derivative somehow by putting a bound on the derivative or a bound on the second derivative? Is the function as a whole convex or strongly convex? Strongly convex means that if your loss function looks like this, you can put so a convex function is always lower bounded by its tangent, and if you can add a little bit of a quadratic to the tangent and still have a lower bound, that means that it's strongly convex. How expensive is it to evaluate each one of the terms, or their gradients, or their second derivatives? What does the constraint set look like? Is it just an arbitrary convex set? Is it a smooth set? Or is it maybe the simplest possible one is a subspace? Is it a set of linear equality constraints? How accurately do we need to know the optimal weight vector? Or how much hardware can we afford, right? If we can afford just one processor on our machine versus if we can afford an entire data center, that opens up different algorithms. Same thing, we might have a hard real-time constraint. We might have to answer every machine learning problem, answer every prediction in a millisecond, or we might even have to solve the entire learning problem in a millisecond. Or we might have an hour or a week. And a lot of times we can set up the problem in a lot of different ways, and that can lead to differences in the properties above. And depending on how we set it up, that's going to affect what algorithms are effective at solving it. And this is, like I said, a really rich and deep area. You can take an entire semester-long course on this subject. You can take several. But if you're interested in this sort of thing, I'd recommend there's a course 10725, which is convex optimization with a machine learning focus. And it's a nice course for people who are interested in this sort of thing. Now I wanted to point out one more thing if we go back up to the problem formulation. So here I've broken out L0 from the rest of the loss functions. And one of the ways that you can be different about setting up the problem is you can choose to group all of the terms with some set of properties, like being non-smooth or being strongly convex. You can choose to group them all into L0 and then group the remaining terms into the LT. Or, for example, if you have a strong ridge term here, you can keep it as L0, or you can break it up into T pieces and include it with each one of the little LTs. And depending on how you do that, all right, the audio is cutting again, so I'm going to stop and restart the stream. Hopefully that seems to have fixed it in general before. All right, so hopefully we're back, and hopefully the streaming is going to be better this time around. Let's get back to the slides. So what I was saying before I cut out was up here in this loss function. You can group terms differently, and you'll wind up with different optimization setups. Maybe for today's lecture, the most important thing is that if you have a ridge term, which is large compared to all of the little individual loss functions, you could break up the ridge term and include 1/t of the ridge term in each one of the little loss functions. And we'll see in a little while why that's important. All right, so in particular, one of the things that is true about optimization problems in machine learning that's maybe very different from other fields is that we don't always want necessarily a particularly accurate solution to our optimization problem, because we don't directly care about the solution, we care about the predictions we make in the end. So if we can solve the problem less accurately and get just as good or perhaps even better predictions, we're perfectly fine with that. And so that's different from how a lot of other fields would view optimization problems. And it leads to a couple of consequences. One of the consequences is that we can use what's called early stopping, meaning that we run an incremental and iterative optimization algorithm, and instead of running it forever or running it until it converges, we just stop it early. And we'll see an example of this below. The second is required accuracy. So again, in some other fields, they might want machine precision for the parameters W. They might want to have them accurate to 1 part in 10 to the minus 1 part in 10 to the 12. So a relative error of 10 to the minus 12. In machine learning, we could ask for that, but that might actually be useless, right? So our optimization problems are generated from noisy data. And if we have a limited amount of data, then there's just a limited amount of accuracy in the W that we get at the end, irrespective of how accurately we solve the optimization problem. So if we solve the optimization problem to, let's say 3 significant figures, that might be plenty good enough. And any more effort that we put into the optimizer could be wasted. And the reason that's important is that it opens up a different set of optimization algorithms. We can use optimization algorithms that don't converge as quickly, especially don't get really high accuracy as quickly, and they'll be good enough for our purposes. All right, so that's enough generalities. Let's get to a specific algorithm. And that specific algorithm is, in many ways, everybody's favorite, stochastic gradient descent. And the reason it's everybody's favorite is that it's really pretty much a a jack of all trades. It can solve a huge variety of machine learning optimization problems, and it can solve them all pretty well. It may not necessarily be the best for some application, but it's often, the second or third best, right? It's often a very reasonable thing to do. And it's also very simple to implement, although, as we'll see below, there are some decisions, some interesting and maybe difficult decisions we have to make. So there's a really simple fact about gradients, and gradient descent and stochastic gradient descent are based on that. And that fact is that the gradient is the direction of instantaneous steepest ascent, meaning it's the direction locally in which the function increases as rapidly as possible. So let's have a look at a loss function. Suppose this were a loss function, right? So the two horizontal dimensions are w, right? They're the parameter, and the vertical dimension is the loss as a function of w. And so what we're hoping to do is to get to the lowest point, which is right here on the loss function, or maybe just to a local optimum, which is the lowest point in a neighborhood. By the way, I should define, everybody says local optimum, but I should define it precisely. A local optimum is a w such that there exists a neighborhood, which I'm going to write as just a ball of radius epsilon, which is strictly greater than 0, such that L of w is less than or equal to L of w prime for all w prime such that the distance between w prime and w is less than epsilon, right? So there's a strictly positive epsilon such that in the open ball around w, w is the smallest value of L, right? And so you can see that this here is a local optimum. This is also a local optimum, and in fact it's the global optimum, meaning that it's the local optimum with the smallest value of L of w. All right, so if we take the, this is just the contour plot, right? So I put a contour plot on the axes and then showed the loss function draped above it. But if you just show this contour plot and you pick a particular point, w, right there where the cursor is, right here, and you draw its gradient as a vector, that's the blue arrow, right? That gradient is going to be a direction in which the function is increasing rapidly. And if you look at the hyperplane that's normal to the gradient, which is this blue line right here, that hyperplane is, at least locally, a place where the loss is constant. And if you're on this side of the hyperplane, the function is increasing, and if you're on this side, the function is decreasing, again, locally. And so if you define the level set to be the set of points where L of w equals L of w0, and if you define the Taylor expansion of L, which is this, right? It's L of w0 plus w minus w0 dot the gradient at w0. You can explain this behavior, right? Because the Taylor expansion says, at least approximately, that L of w minus L of w0, so the increase in w, will be positive exactly when this term is positive, meaning that your difference from w0 has a positive dot product with the gradient. And having a positive dot product with the gradient means exactly that you're on this side of the hyperplane, and having a negative dot product with the gradient means you're here, and the hyperplane is exactly where you have 0 dot product. All right. So the interpretation of the gradient as the direction of steepest descent suggests a really simple algorithm. You decrease L as rapidly as possible if we move in the opposite direction from the gradient. So we just update w to w minus eta times the gradient. And eta here is called the learning rate or the step size, and it has to be non-negative. and we have to choose it to trade off between large eta, where we move quickly, make big updates, and small eta, where we make gradual updates, which means that the Taylor approximation is still a good approximation over the length of our update, which we want because if the Taylor approximation stops being good, then we might not actually decrease W when we take our step, right? So gradient descent is just to iterate this update over and over. And I want to say you probably shouldn't really use gradient descent for anything but the smallest problems. There are better algorithms. Well, there are better algorithms for almost every case, but gradient descent has the advantage of simplicity, right? It's like one line of pseudocode and maybe 2 lines of Matlab. Now, the reason that the reason that gradient descent is not a good idea is that it could take a really long time to evaluate the gradient, right? So if you remember the definition of L was L0 plus the sum of the little LTs. So the gradient of L is the gradient of L0 plus the sums of the gradients of the little LTs. And if big T is large, meaning that we have a ton of terms, for example, a lot of training examples in maximum likelihood or a lot of training examples in linear regression, then just iterating over all of these terms to calculate the gradient could take a prohibitively long time. And so to mitigate this problem, we go to stochastic gradient descent. So L of W is still going to, if you look at the Taylor expansion, right, it says that as long as you move in approximately the same direction as the negative gradient, you're going to still decrease, you're going to still decrease the loss. At least you're going to decrease the Taylor approximation. So if you take a small learning rate, you'll decrease the loss as well. On average, right? Any individual step might increase the loss if you're unlucky, but on average, you're going to decrease it. And to see why that works, so let's consider that we take a step eta times g, where g is some approximation to the gradient, right? So the expected value of g is equal to the gradient, but g might itself be noisy. So if we take the expected value of L of W minus eta g, where the expected value is over the randomness in g, well, you can say that that's approximately equal to the value if you substitute in the Taylor approximation, right? So that's L of W minus eta g dot grad L at W. And then by linearity of expectation, that means that you can push the expectation inward and get eta times the expected value of g. And then the expected value of g is just grad L by assumption. And so that is the norm squared of grad L. And anything squared is positive. So here we've decreased L compared to L of W, right? So on average, we'll go down if we take a small enough learning rate that the Taylor approximation is accurate. So that's kind of cool. And so all we have to do is then find a way to get an approximate gradient much more efficiently than evaluating the exact gradient. And then we'll be able to update W much more often than we would with ordinary gradient descent. And so every individual update might not be as effective, but because we're doing so many more of them, we'll make up for the loss in accuracy. And in fact, it turns out that the fact that the update has a little bit of randomness in it can even be beneficial. It can help us explore the loss function and keep us from getting stuck in local optima. So fortunately, it turns out to be really easy to find a vector g that approximates the gradient. All we have to do is choose a single term randomly from our sum and then scale by the number of terms. So if we take our index I uniformly distributed in 0 through t, right, then the expected value of the gradient of Li of W given W, that's equal to the probability, the sum over all possible values that I could take. So I'm going to sum from t equals 0 to big T, of the probability of getting that value of I, which is 1 over t plus 1, times the value of our random variable, which is the gradient of LT of W, given that I equals T. And so if we multiply this by T plus 1, the expected value of T plus 1 times the gradient is just the sum from 0 to T of grad LT of W, which is the gradient of big L of W. And so if we use that approximation, if we use that way of getting a noisy sampled gradient, we get the stochastic gradient descent algorithm, which, to summarize, is just repeatedly sample an index uniformly from all of our terms and update according to that index. And I should say here, if L0 is much larger than all of the other terms, what we would like to do is break L0 up into T pieces and include one of the pieces with each of the individual terms. So instead of L0 is equal to lambda over 2 and LT is equal to YT minus W dot XT squared, right? Instead of that, we can do L0 is just the constant 0, and LT is equal to lambda over 2t norm of W squared plus YT minus W dot XT squared. And let's actually put a half in front of both of those terms there. All right, so this makes sense. And the reason for doing this, you can see by looking here, the variance of our gradient estimate is going to depend on the relative scales of the gradients of each of the loss functions. And so if the gradient of L0 is way bigger than the gradients of all of the other ones, we're going to get a larger than necessary variance in our estimate of G. All right, so that's stochastic gradient. A lot of people have probably already heard of it. And if you've heard of it, one of the things that you've probably heard is that it can be difficult to tune the parameters. So there are two main parameters that we need to tune in SGD. One is the learning rate, eta, and the other is the total number of iterations that we run for. And in fact, it's a little bit more complicated than that, because we don't just want to select a single learning rate eta. We typically want to adjust the learning rate eta over the course of our optimization. Typically, we'll want a larger learning rate at the beginning and a smaller learning rate at the end. And the reason for that is that in the beginning, you're going to be, let's say that, in the beginning we start over here at W, and the optimum is, let's say, way over here. We'll call it W star. Right? And our gradient samples will mostly all point in the general direction of W star. There might be a couple, right, that point in different directions, but by and large, most of them will point in the general direction of W star. Right? And so that means we can take a big learning rate because most of the time we'll be moving in the right direction. On the other hand, if we're over here, closer to W star, right, so we'll call this, W0, the first one, and this one will be WT, where we're close to the optimum. Then, because we're close to W star, the overall gradient is close to 0. And in order to sum out to 0, the gradients, the individual gradient samples have to be pointing in different directions. And so we'll get, gradients that point like that, right, in all different directions. And maybe, we'll get a few more that are pointing towards W star, right? But it's going to be much noisier, and so we need a much smaller learning rate in this situation than we did in that situation. So how do we tune stochastic gradient descent? By far, the most common way these days, and probably the best way that I know of, is to use holdout data. So we start with a relatively large value of the learning rate, and we monitor our error on a separate holdout set, meaning that we calculate the loss function L sub holdout on an independent sample of data. You can also use cross-validation or bootstrap if you prefer, but holdout is faster, and faster is good for stochastic gradient. And when the holdout stops decreasing on average, we reduce the learning rate. Say we divide it by 2. And then when it stops, the error on the holdout stops decreasing on average even after we reduce eta 1 or 2 times. Then we stop the algorithm as a whole, and we just return the value of W that scored the best on the holdout set. And this, by the way, is the early stopping method that I mentioned earlier, right? So we don't run all the way to the optimum on the training set. We just run until the error stops decreasing on the test set, or the holdout set. So because the stochastic gradient updates are noisy, we expect that the holdout error is not going to go straight down. It's going to fluctuate around. And also, it costs something to compute the holdout error. And so what that means is that we... Oh, somebody is asking, can you change the learning rate as you go? Yes, definitely. We want to change the learning rate as we go. So like I was saying, we typically want to start with a large step size towards the beginning of the optimization and go to a smaller step size towards the end. That's this picture right here. I suspect that what happened is that question was delayed because of the streaming. All right, so... Right, okay, so it's expensive to compute the holdout compared to an iteration of stochastic gradient, and so we don't test for a decrease in the holdout error on every iteration. Instead, we do it every delta iterations. And delta just needs to be a big enough number. The consequence of making it too big is just that you go too slowly, right? You don't do it often enough. And so you just make it so that the work for delta iterations of SGD is large compared to the work for computing the loss on the holdout set. Somebody says, why are we choosing a single term randomly? Aren't we just going to go through the entire training data and update the weights in each iteration? If we did that, if we went through the entire training data and then updated the weights, that would be gradient descent. You would be calculating the exact gradient of the loss function. And gradient descent is too expensive if we have lots of training data. So what we're doing is we're sampling indices randomly to get a noisy approximation of the gradient, right? That's this derivation in section 7 here. If we sample a single index I uniformly in 0 through t and take the gradient of Li of W, then this derivation shows that the expected value of that, if we scale it appropriately, is the full gradient, right? And then this derivation up here shows that it's enough to have a noisy sample of the gradient, right? To pick one term and take only its gradient that will still, on average, decrease our loss function, right? So that difference, the difference between iterating over all of our training data versus selecting a single index randomly, that's the difference between plane gradient descent and stochastic gradient descent. And like I said, stochastic gradient descent can often be a lot more effective than plane gradient descent, just because it's so much faster to compute the stochastic gradient. All right, so to summarize, in order to run stochastic gradient, what we do is we initialize W to something reasonable, maybe to all zeros or to a vector of small random numbers. We initialize our learning rate to something that makes eta times the norm of the gradient be a reasonable value, say 1 or 0.1. Or maybe even 10 to the minus 3, right? Like the initial value of eta is something that it's hard to tune as well, but it's less important if we have a method of reducing eta if we happen to select one too large. All right, so we initialize W, we initialize eta, we repeat the update, randomly select a training example, compute the gradient of the loss just on that training example, and take a step in the direction of the negative gradient. Then every capital delta iterations, we evaluate the loss of our current W on our holdout data, and if that loss is decreasing, all good. And if it stops decreasing, we reduce our learning rate and try again. And then if after we reduce our learning rate, it still doesn't stop, decrease some more, then we're done. And we return the weights that had the best error on the holdout set. All right. So what I wanted to do was to give you guys a little bit of a chance to play with gradient descent. And so what I'm doing is I am posting to Piazza all right, there you guys go. So you should be able to go on Piazza and download a zip file that has two, there are two files in the zip archive. One is x.csv, the other is y.csv. And so if you unpack them and load them into your favorite language, we're going to be able to play with gradient descent. And I will also go ahead and post some code to get you guys started. All right, so I've updated the post if you want to reload it so that it has Matlab code for loading the data and splitting into train and validation. And let's see, I think what I can do I can also post some code for gradient descent. So I'll edit the post again so that you guys have some starter code for gradient descent. All right. So everybody should have a look at the post. Download the data, and what I would suggest is playing with this for a little while in Matlab. So play with the number of iterations and play with the learning rate and see what you guys discover. So there's a parameter in here as well that I'm going to talk about in a sec called the batch size. You can ignore that. Or if you know what batch size is, you can play with that as well. So I'm going to hold off for a second, and please download the code, play with it. Feel free to translate it into NumPy if you prefer that, and let me know any questions that you have. Oh, I should say, by the way, that the data that you're looking at is some images. So the X's are images of digits, and the Y's are indicators of what the identity of the digit is. So they're all digits. I think I used 1 to 4. And the image is a 28 by 28 image. And if you're interested, this is a subset of the MNIST data. All right, so we're back now. I wanted to, so hopefully you guys have had a little bit of a chance to play with this. I wanted to show you a little bit of what happens. So here's what I've done. I've added some code to the end of the post that lets you visualize your learned weight vectors. So here's an example. What I've done is I've taken the weights, and these are the weights that, this is the row of the weight matrix that we use to predict whether it's a 4, right? So this is the row where if you have a large dot product with this row, then you're likely to be a 4. And you can sort of see there's a noisy 4, right, in the middle of it in positive weights, and then negative weights where the other digits tend to be positive. And if you go, again, there's code for making this plot in the Piazza post. And if we try, here's what the 1 looks like. And you can see that it's positive in the vertical bar in the center where there's a 1. Here's the 2. You can sort of see a 2 there, right? So it's kind of interesting, right? Gradient descent has done something useful. All right, so continue to play with the gradient descent. I think actually because we're getting close to the end of the lecture, I'm not going to ask you guys to hand in anything today. I will probably ask for a hand in related to this exercise after Wednesday's class. And I will I'll update the post on Piazza with what you'll need to hand in. But for now, no hand in, and I'll update the post on Piazza to say that. All right, so let's keep going. So remember that in stochastic gradient descent, instead of looking at a single term at a time, or in stochastic gradient descent, the vanilla version of stochastic gradient descent, we looked at just a single randomly selected term at a time. If we want to, we can instead sample B of them at once and take the average of their gradients, right? Okay, so why would we do that? Oh, by the way, if we take a group of B of these gradients at once, that's called a mini batch. And why would we want to do a mini batch? Well, we can average out the noise in our gradient samples. We can get G using this definition is going to be less noisy than G using the definition from the previous section. And so that'll let us use a larger learning rate eta. Now, if we do a back of the envelope calculation, we have a mini batch of size B that will reduce the variance of G by a factor of B, and that lets us use a learning rate B times larger. But we have to calculate B times as many gradients in order to do a mini batch. So it seems like we're going to make B times the progress, because we use a larger learning rate, at B times the cost, because we're touching more training examples. And so mini batches, naively at least, seem like they shouldn't speed up stochastic gradient at all. They shouldn't hurt it much, but they shouldn't speed it up. And if you think about it a little bit more, in ordinary gradient descent, we calculate each new gradient at the latest value of W, whereas with mini batches, we calculate them all at the same value of W, which is good for the first one, but for the second and subsequent ones, that value of W is a little bit out of date. So that should hurt a little bit. So why would you ever use mini batches? Well, it turns out, especially if you're using a high-level language like Matlab or Python, mini batches are a great thing because you can use fast matrix operations to calculate all of your gradients, and that means you can do them much faster when you do B of them at a time than you could when you're doing one at a time. And by fast matrix operations, I mean, you call out of Matlab to the matrix operations in Matlab, which are implemented in Fortran, right? Or you call out of NumPy to the same BLAST library that's implemented in Fortran. Or better yet, you have a graphics card in your system and you push all of your matrix multiplies, all of your dot products over to your graphics card. And graphics cards are optimized for regular loops like computing tons of big dot products. So you have to pay actually much, much less than b times the cost to compute b gradients. And so mini batches can be a win for that reason. The other reason that mini batches can be interesting is that we get b different gradient samples at once, and we can look at statistics of that set of b gradient samples. And in a little while, we'll see how that can help us. All right, so stochastic gradient is wonderful. What could possibly go wrong? The single biggest thing that can go wrong in stochastic gradient is what's called a poorly conditioned problem. So the condition number of a problem is the ratio between the largest and smallest eigenvalues of its Hessian matrix, right? So if you take a loss function and you take its first derivative and then its second derivative, the second derivative is a matrix. It's a symmetric matrix, and it's PSD if the problem is convex. And if you look at the if it's convex, meaning all of the eigenvalues are bigger than or equal to 0, the condition number is the ratio between the largest and the smallest eigenvalue of the Hessian. And that's the condition number at a particular point, and the condition number of a problem is the worst case over all points. So the condition number is always bigger than 1, because the largest eigenvalue is always bigger than the smallest eigenvalue. And if the largest eigenvalue is close to the smallest eigenvalue, that gives you a small condition number, a small ratio, which is good. And if the largest eigenvalue is much larger than the smallest one, that gives you a bad condition number, meaning a large condition number. And, okay, eigenvalues, whatever, right? What does that mean in practice? Here's a contour plot of a well-conditioned problem, and you can see the contours are fairly close to round. Right? They're not, longer in one direction than the other. And here's a somewhat more poorly conditioned problem where the contours are long and skinny, right? And in a well-conditioned problem, gradient descent and stochastic gradient will tend to head straight for the minimum. And in a poorly conditioned problem, they'll bounce around a lot. And in particular, a lot of the updates will be in directions that cancel each other out, and you'll move slowly. So here is a plot of what happens if you run, this is actually gradient descent, but the same thing happens if you run stochastic gradient descent. So here's the number of iterations on the x-axis. On the y-axis is the difference in function value between the current iterate and the optimum. So you'd like for it to be very small. And it's on a log scale. And you can see that for the poorly conditioned problem, gradient descent goes down slowly, and for the better conditioned problem, it goes down much faster. All right. So what can we do about a poorly conditioned problem? So the first thing is, if we knew the Hessian matrix, we could transform the problem to a problem with a better condition number. So I'm not going to go through the math because it's right here, and it's sort of easier to follow the math by going through it right here than it is by my talking it. But if you transform the problem, you start with the Hessian matrix, and you invert it and take its square root. So you call A the matrix such that A times A transpose is equal to the inverse Hessian. There are multiple square roots, and you can use any one of them. It doesn't matter. And then you transform the problem by taking L of AW prime instead of L of W, right? Where W prime is A inverse W, right? So this is the same problem, right? You can have it as a function of W or as a function of W prime. But if we do it as a function of W prime and calculate the Hessian, you get the identity. And all of the eigenvalues of the identity are 1, meaning that the condition number of 1, the condition number is 1, which is perfect, at least in the neighborhood of the point where you evaluated the Hessian. And so if you run gradient descent on this transformed problem, we get an algorithm called Newton's method. And Newton's method takes many, many, many fewer iterations than gradient descent. like in a problem where it could take hundreds of iterations of gradient descent, maybe 10 iterations of Newton's method might be enough. The problem, of course, is that you had to compute and factor the Hessian, which is expensive, right? So if it turns out that you have few terms in your loss function and few dimensions in your parameter vector W, Newton's method is a great idea. But in a lot of machine learning problems, that's not the case, and so we're not really recommending Newton's method. But Newton's method gives us an idea, which is that if we know the Hessian exactly, we can get a great condition number. But what if we have a cheap but only somewhat accurate approximation of the square root of the inverse Hessian? We can still do the same trick. We can replace W by A inverse W. And we can we can replace W by A inverse W, which is W prime. And we can run SGD on the transformed problem. And if we got a decent approximation to the square root of the inverse Hessian, then stochastic gradient will converge faster on the new problem than it did on the old one. And this strategy is called preconditioning, taking a linear transformation of your variable in order to try and get a better condition problem so that SGD will converge faster. So how do we get our preconditioner, our approximate square root of the inverse Hessian? And there are, as it turns out, a bunch of ways, because this is an important problem and numerical analysts have been working on it for the last half of a century at least. But a lot of the popular and effective ones are based on one of two interesting properties of the Hessian. The first property is that the Hessian is related to the variance of our gradient samples. This is not at all obvious. It's kind of a deep property. And you can look at the proof online, but the proof's beyond the scope of this class. What we have to know for this class is just that there is a relationship. In particular, we can define the Fisher information matrix I of W to be the expected value of the outer product of the gradient with itself at that point W. If we sample terms if we sample the x's at which we evaluate the gradient from the probability distribution parameterized with W. So let me say that again. We have a loss function L. Let's suppose that that loss function is a log likelihood. So it's the sum over a bunch of samples of the probability of the log probability of x given the parameter W. So if that's the case, then if we have the true W and we sample x's according to that W and we evaluate this expectation, the expected outer product of the gradient with itself, that's called the Fisher information matrix. And if our loss function is sufficiently smooth, the information matrix is actually equal to the negative Hessian of the log likelihood, which is, like I said, deep and maybe unexpected, but it's true. And something similar also holds if it's a log conditional likelihood instead of a log likelihood. So to take advantage of this property, what we can do is we can approximate the information matrix by taking the average of the outer product of the gradient with itself over our training data. And this is not a perfect approximation for two reasons. The minor problem is that there's sampling noise. The more major seeming problem is that our training data was presumably not sampled from the current W, because if we knew the current W, we wouldn't have, if the current W were the true W, we wouldn't have to optimize, right? So the training data is presumably sampled from a distribution parameterized by a different value of W. But it turns out that that's okay, that if we can still use the Fisher information matrix to approximate the Hessian. and it actually makes the optimization more robust, that we're using essentially the fact that we're using the Fisher information matrix based on the true samples from the true distribution instead of the distribution as parameterized by our current W. All right, so that's the Fisher information matrix. And we can then approximate the Hessian with the Fisher information matrix, take its inverse, take its square root, and use that to make a preconditioner for gradient descent, or for stochastic gradient descent. If we do it for gradient descent, we get an algorithm called Fisher scoring. And if we do it for a stochastic gradient descent, we get natural stochastic gradient descent. All right. So going back to Newton's method, right? What Newton's method looks like is right, at every iteration, we compute the Hessian, we use it to compute a preconditioner, we make the transformation, we make an update, and then we undo the transformation, and we start over, right? So that's Newton's method. And in Fisher scoring, we do the same thing, except that instead of the Hessian matrix, we take the Fisher information matrix, right? And now, if we're doing plain gradient descent, it's perfectly fine to compute the Fisher information matrix because we had to iterate over all of our training examples anyway to compute the gradient. If we're doing stochastic gradient descent, we have to, it's expensive to compute the Fisher information matrix. And so what we would want to do is do it only every so often. Update the Fisher information matrix when we think that our current information matrix is out of date. And there are, other strategies which are problem specific, but a good general purpose strategy is to update it only every so often. All right, so the second property of the Hessian that's useful is that it tells us how the gradient changes as we change W. So suppose that we approximate the loss locally with a quadratic, right? 1/2 W transpose HW plus G transpose W plus C. So C is a constant, G is the gradient vector, and H is the Hessian. So if we take the gradient of that, we get HW plus G. And that means that if we take any two values of our parameter vector, call them W and W prime, and we look at the difference in the gradients, that's equal to the difference in HW plus G, which is H times W minus W prime, right? So if we record the difference in gradients, and we record the difference in parameter vectors, and we do that a whole bunch of times, we get a bunch of linear equations that we can solve for the Hessian. And if we do it, if we do it a whole bunch of times so that it's an overdetermined set of equations, we would use linear regression instead of just solving a set of linear equations. In the exact case, if W is a d-dimensional vector, then we need d samples to recover the Hessian. In practice, the loss function is not going to be exactly quadratic, and we'll only get noisy samples of the gradient, and so we'll need substantially more than d samples to estimate the Hessian. And so we can use this property to build a preconditioner for gradient descent or for stochastic gradient. Right, so we just record a whole bunch of gradient differences, a whole bunch of W differences, and solve for H to get our preconditioner. And if we do that for gradient descent, we get a method called BFGS, after the authors Broyden, Fletcher, Goldfarb, and Shano. And if we do it for stochastic gradient, it turns out there's a way to update the estimate of the Hessian online with stochastic samples of the gradient, and that's called online BFGS. All right, so these descriptions, by the way, in section 13 and 14 of Fisher scoring and BFGS, they are intentionally very high level. You can get the actual code for these methods in a lot of places. The thing that you should take out of sections 13 and 14 is that we're using two different properties of the Hessian to be able to get approximations based on gradient samples. And then once we have these approximations, we can use them to derive preconditioners. All right. So, I think we are, rather than starting the next section, I think we're basically getting close to the end of class. So I will continue with these notes on Wednesday. And keep playing with the stochastic gradient code that I posted, and give me questions in office hours. Office hours start now, or post questions on Piazza. So we'll see you guys on Wednesday.